This video models some answers to typical past paper questions for Combined Science Physics Paper 1. I'm specifically looking at the particles topic this time and around about grades 4 to 5 in terms of the level of the questions. Let's start with question 1. So to start off with, we're looking at solids, liquids and gases. We're asked to describe, so we're describing, not explaining, the difference between solid and gas states. So look very carefully, because although it says solids, liquids and gases at the top, it's asking us to describe what happens to solid and gas states only. It's then asking us to describe them in terms of the arrangement of the particles and the movement of the particles. So it's also a 4-mark question. And remember, if you look at the question, it's directing us exactly what it wants us to do for those 4 marks. So I need to write about solids and gases, and I've got 4 points to make because there are 4 marks. So 2 of those are going to be about solids and 2 of them are going to be about gases. So these first 2 points here need to cover solids, and these 2 points here will need to cover gases. If I do that, then I've done this part of the question. It also tells me I've got to talk about arrangement and movement. So the first sentence I need to write about solids is about the arrangement of the particles. So the arrangement is that they are arranged regularly, or they're close together. And then the second mark will have to be about movement. So they vibrate around fixed points. So looking at gases now, again, I need to talk about arrangement and I need to talk about movement. So the arrangement then is that they are spread out. And in terms of the movement, then they are moving rapidly and randomly. So by looking at the question and breaking down exactly what it's asked for, I can see exactly where my 4 marks are going to come from. I've done 2 marks of solids and gases, and I've mentioned arrangement and movement for each of those. Part B, what is meant by specific latent heat of vaporization? This is just a definition that you need to learn. So it's the energy required now, specific latent heat is always the energy required to change state, but notice we're asked about vaporization. So we're specifically looking at changing state from a liquid to a gas. So it's required to change 1 kilogram of a substance. So I've got my first mark there, and then the vaporization from a liquid to a gas. And there's the 2 marks. Part C then, while a kettle boils, 0.018 kilograms of water changes to steam. There's one of our givens. We're asked to calculate, that's our command word, the energy. There's the unknown we're looking for, and we're also given the specific latent heat of water. So I know what my givens and unknown is. I've now got to identify the correct equation. So I'm looking for something which has energy in and mass and specific latent heat. If I go to my equation sheet, there's only one that even has specific latent heat in, which makes it nice and easy, and that's energy equals mass multiplied by specific latent heat. So let's put the numbers in. I've got the mass is 0.018 and the specific latent heat is 2.3 times 10 to the 6. So make sure you understand your standard form and know how to use it on your calculator. If I complete that calculation, I get 41,400 joules. And so there's our answer. In this case, they're quite happy for you to round that to 2 significant figures. They'd also accept your answer in standard form, as there's standard form as part of the question. Part D, We've got a graph here showing how temperature varies with time down on the bottom right there. It's not drawn to scale, it's just showing qualitatively what happens, and we're asked to explain. So explain what has happened to the substance in sections A, B and B, C. Now the important point to note here is that we've got 4 marks and we're asked about 2 sections. So we need to write 2 separate points for each section of the graph. So again, it's always worth, before we start answering a question, to look at how many marks there are and how those marks should be divided up. So now let's have a quick look at what is going on the graph. So the first section is A and B. Now most people pick up 2 marks on this question and lose the other 2 marks. So let's have a look at how we can increase our information here. So section AB, what most people correctly say is that it's changing state. So the substance is changing state from a solid to a liquid. Don't forget to say from solid to liquid because that's important. The second part is the bit people quite often forget, which is we need to comment on the fact that it is at a constant temperature. Now it's okay for you to say that the temperature isn't changing, but we need to comment on the fact that that line is flat, so therefore there's no change in temperature. Then if we look at BC, then obviously the temperature is increasing, it's going up, but we mustn't forget it finishes at C, so we need to comment on what is happening at point C specifically. So the first bit here is for saying the temperature of the liquid is increasing. Or we can say that the liquid is getting hotter until, and at point C, that's boiling point, until it reaches boiling point. The important thing to say here is boiling point, because B doesn't sort of finish part way up that slope, it finishes at the point at which the liquid is starting to boil. So most people get the first and the third bullet point, quite a lot forget the second and fourth bullet point. Question 2. Scientist cools air inside a container. We're told that the temperature goes from 20 to 0 Celsius, so it's cooling down. The volume remains the same, so the container isn't expanding or contracting. And then the actual thing we have to do is explain how the motion of the molecules causes the pressure to change. So that's what we're being asked to do. As the container gets cooler, how does the motion of the air molecules cause the pressure to change? So we've got 3 marks, so obviously we've got to have 3 bullet points. So I'm going to start off with my 3 bullet points. So my third bullet point will need to end with how the pressure changes. So I'm going to give 2 of my bullet points over to saying what happens to the motion of the air particles. And then my last one is going to say what the result of that is. So we're going to start off with the fact that the air is getting cooler. So again, if you're not sure about these questions, write down what you know, because you will pick up marks. So we know that as the air gets cooler, the particles are going to be moving less fast, or they're going to have less energy. So I'm going to put in here that the particles have less, and in fact it's kinetic, isn't it, as they cool. So we know that that is definitely a true fact. As a result of that, then, because they're moving less quickly, they've got less energy, they're going to collide less often with the walls of the container. So there's fewer collisions with the wall of the container. So I've spent 2 of my bullet points saying what will happen to the particles when they get cooler and how that affects the collisions with the wall of the container. So my third one is going to be sort of a therefore the pressure is lower. So now when I check back, I've explained how the motion of the air particles causes the pressure to change, and I've also explained what that change is. So I'm fairly confident I've hit all 3 marks. Looking at part B, we've now got a calculation. So we're being told that the air contained water that froze, so we've got a change in state. We know that the energy at that point is 0.7 kilojoules, and we know the specific latent heat of fusion is 330 kilojoules per kilogram, and we're asked to calculate mass of ice produced. So again, we've got to find the correct equation. So I've got an energy here, I've got specific latent heat, those are my givens, my unknown is the mass of ice. So again, I'm looking for an equation that contains all those 3. There's only one, and that is energy is equal to mass times specific latent heat. Now, before I put the numbers in, I need to notice that I've now got kilojoules and I've got kilojoules here. Now, there's 2 ways of looking at this question. If you feel more confident making sure you get the right conversions, then I need to convert 0.7 kilojoules into joules. So that's going to equal 700 joules. Remember, kilo is big, so the number is going to get bigger, and it means I've got to multiply by 1,000 because kilo is 1,000, so I end up with 700 joules. I've also got 330 kilojoules per kilogram over here for my specific latent heat. So again, I need to convert to joules per kilogram. Kilo is large, so I'm going to multiply by 1,000 to get me 330,000 joules per kilogram. Let's put those numbers in. So I've now got 700 is equal to the mass, which I don't know, multiplied by my 330,000. So I'm going to get 1 mark for doing that because I've correctly substituted those numbers in. Now I need to rearrange the equation, so hopefully I can see by laying that out I've got to do a division. I'm going to have to divide both sides by 330,000. So I've got 700 divided by 330,000 will equal my mass, and it comes out as 0.00, and it's 21 recurring. Okay, so I'm going to get a 2nd mark for the correct rearrangement and a 3rd mark for the correct answer. Now it's quite fine here to just put 0.0021 and just give that to 2 significant figures. Okay, you may spot as well that there is an alternative way of looking at this. Because I've got kilojoules and kilojoules on both sides, actually I can just leave it as 0.7 equals m times 330. I'd therefore do 0.7 divided by 330, and that would give me the same answer. And that's because, in effect, I've got times 1,000 on both sides of the equation when I've converted. So if you feel really confident about units, you could just do this. If you're not, then I'd convert, because at least then you are avoiding making mistakes in your conversions. Let's see. This question, in terms of the understanding of the physics, is really simple because we all know what boiling and freezing and so on are. It's sort of difficult because it's like a horrible logic puzzle. So I'm just going to show you how I go about answering this one. So we're told that the air in our container also contains oxygen, nitrogen and carbon dioxide. And then we're given this information. So oxygen is going to boil at minus 183 and freeze at minus 218. Then we're told that nitrogen boils at minus 195 and it freezes at minus 210, and carbon dioxide sublimates at minus 78. Remember, sublimate means it goes straight from a gas to a solid. It doesn't go through a liquid phase. So the scientist cools the air to minus 190 Celsius. What is the state of each substance at minus 190 Celsius? So in a way, it's quite a simple question because we're just working out whether it's solid, liquid or gas at minus 190. But with all that data there, it can get a bit confusing. So the way I look at it is this. If I look at each of these in turn, I'm going to look at oxygen, I'm going to look at nitrogen, and I'm going to look at carbon dioxide. And then I'm just going to pull out the fact that I know that the boiling point for oxygen is going to be minus 183, and its freezing point is at minus 218. If I look at nitrogen, my boiling point is going to be at minus 195, and my freezing point is going to be at minus 210, and then carbon dioxide just sublimates at minus 78. So if I consider what that really means, then once you've boiled, you become a gas. This is a gas. This is a gas. Between the freezing and boiling point, you're going to be a liquid. And then once you've frozen, you become a solid. And then carbon dioxide already goes straight to solid. So that's what's happening. Now let's have a look at what happens at minus 190 degrees. So minus 190 degrees for oxygen is going to sit in this region here, because it's going to be lower than minus 183, but higher than minus 218. If I look at nitrogen, minus 190 is going to be up here, because it's not as far down as minus 195. And then if I look at carbon dioxide, minus 190 is going to sit down here, because it's much lower than minus 78. So that tells me that oxygen is going to be a liquid at that point, at that temperature. Nitrogen will be a gas at that temperature, and carbon dioxide will be a solid at that temperature. So rather than trying to sort of just work out what's going on with the numbers in my head, I find doing a little diagram and thinking about it that way means I'm much less likely to make a mistake. So if I then go to my tick list, my oxygen is a liquid, my nitrogen is a gas, and my carbon dioxide is a solid. Part D, the air also contains a small amount of argon, and as the temperature decreases from 20 to minus 190, the argon changes from a gas to a solid to a liquid. Explain the changes in the arrangement and the movement of the particles. So this is very similar to a previous question. And again, before I start writing anything down, I'm going to take a bit of time to plan my answer. So I've got gas, liquid and solid, and I've got 6 marks. So that means I need to write 2 points about a gas. I need to include 2 points about the argon as a liquid. And I need to include 2 points about argon as a solid. And it says explain the changes in the arrangement and the movement. So again, for each of those 2 points, I need to include something about the arrangement and something about the movement of the particles. A question like this could also ask you to write in clear English, in which case I'd like to see a bit of a link going from each section to each section, so from gas down to liquid to solid. So in terms of what we can include here, if we look at the arrangement of the gas particles, we can talk about the fact that the particles are spread out, and of course they're moving rapidly and randomly. And what I can include at this point is that they slow as they cool. Now, again, when you're writing this out properly, you need to state that gas particles are spread out, or you need to put gas on the left-hand side here to make it clear what you're writing about. So gas particles are spread out, gas particles are moving rapidly and randomly, and they slow as they cool. Now we're going to go down to liquid. So when we talk about the arrangement, the particles are going to get very close together. So rather than being spread out, they're now very close together. I've covered arrangement, and we need to talk about the fact that they are slower but able to swap places or slide past each other. And then finally getting down to a solid, we now need to talk about how the arrangement changes and how the movement changes. So the particles are now close and regularly arranged. So in the liquid, they're still a little bit random, but now they're in this regular arrangement as a solid, and they are now in fixed positions only vibrating, or vibrating about fixed positions. So you can see there, by looking at the fact it's 6 marks, by looking at the fact I've got to write about solid, liquid and gas, and I've got to break each of those sections into arrangement of movement, I can make sure I cover my 6 marks. It's quite an easy question, this. It's the planning that takes more effort than perhaps knowing the knowledge part. Question 3. We're looking at heat transfer through a single glazed window. And first of all, just name the process. So it's a nice, easy one, this. We just got to remember the name of the process, which of course is conduction. Remember, conduction is how heat energy is transferred through solids. The next question then says explain. So we've got to put a little bit more detail in here. Explain how that heat is transferred. So we've named the process. We now need to describe it. Again, look out for the fact there's 2 marks here. So I need to say at least 2 separate things. I'm going to put 2 bullet points to make sure I do that. So the first point is going to be for something like the atoms in the solid or in the window or in the glass gain energy. Or you could say vibrate more or vibrate with a greater amplitude, but you can say they gain energy. And then for the second mark, we need to have something about the fact that they collide with their neighbours or with neighbouring particles and transfer that energy on. And there we go, that's our 2 parts. Part B, we've got a graph here showing the rate of heat transfer through a window and how it depends on the difference between the inside and outside temperatures. So we've got rate of heat transfer here, and we've got temperature difference down here. First thing we're asked then is what is the range? So we just need to state the range of temperatures. Now again, it sounds a bit daft, but sometimes people put the wrong number. So we're looking at the temperature, not the rate of heat transfer. So that means we're going from 5 degrees Celsius to 25 degrees Celsius. The next bit then, the student looks at the graph and concludes doubling the temperature difference doubles the rate of heat transfer. So you can see we're referring to those 2 axes there. We've got to use data from the graph, so you must use some numbers from that graph and state them. So there's you can use any numbers here really, but I'm going to go from 10 to 20 on the bottom. So I'm going to double the temperature from 10 to 20. If I read off the rate of heat transfer each case, and again it's really worth showing this when you're writing on your exam paper so the examiner can really clearly see your thought process. You'll find it easier because you'll have a pencil and ruler, not an electronic pen, but so you'll get a much better straight line than I will. But you can see that the heat energy transfer goes from 60 to 120, so it clearly doubles. So it's worth putting it on the graph because the examiner can see you're working, but then state as the temperature doubles from 10 to 20 Celsius, the rate of heat energy transfer doubles from 60 to 120 joules per second. So you must put in some numbers there because it does say use data from the graph. Now I've chosen 10 to 20, but you could have gone from any number. So if you double 5 to 10, you'll also see that it doubles from 30 to 60 and so on. So Any numbers will do, but make sure you quote the numbers in your answer. So, third part of this question, we're told here the total area of the windows is 15 meters squared. Now, you need to remember that on the other part of the question, they told us that the information on this graph is for a 1 meter squared window. We're now looking at a house with a total windows of 15 meters squared. We're then told that the temperature difference on this particular day is 20 Celsius. So remember, our graph is showing temperature difference. We're going to be homing in on 20 Celsius. So once again, with some of these questions, if you're not sure what to do, highlight what we know and have a look and see what you can do with that. So we've got to work out the total rate of heat energy transfer through all of the windows on that particular day. Now again, rate of heat energy transfer is this part of the graph here. So let's start off by taking a reading at 20. Now we did that on the previous slide, so it'll be a little bit clearer there. Let's say it's not easy to draw with this electronic pen, but we already know that that's going to give me a heat energy transfer of 120. So at 20 Celsius, we've got 120 joules per second for 1 meter squared. But we've got 15 meters squared, so we're going to have to do 120 multiplied by 15 in order to get our answer for the whole house as opposed to just one window. So when we multiply those two numbers together, we get 1,800 joules per second in total. Question 4. So at the top here, it says that this question, we're going to be assessed on using good English, organising information clearly, and using specialist terms where appropriate. So by organising information clearly, I highly recommend using bullet points, writing full sentences, rather than a long waffly paragraph. The problem with the long paragraphs is you may not pick up all 6 marks, you could end up repeating yourself, contradicting yourself. We know that examiners in the exam boards always report that students who write in bullet points get more marks for these questions. So let's have a look at what we've been asked to do. We've got the arrangement of the solids, liquids and gases as shown in that diagram on the bottom right. We're told to use the diagram and your own knowledge to compare solids, liquids and gases. And we should include information about the arrangement, movement and energy of the particles. So once again, before I start writing anything down, I'm going to plan my answer. We know there's 6 marks, so that means 6 bullet points. So once again, I lay out my answer before I start writing anything and think about what information I'm going to include. Now, because it's solids, liquids and gases, I'm going to recommend once again, we're going to use 2 of those bullet points to talk about solids, 2 to talk about liquids and 2 to talk about gases. And you'll notice that we can talk about arrangement, movement and energy. Now, if I did that for all of those 3, that's 9 possible pieces of information I can include there. And we've only got 6 marks. So you've got a lot of information to choose from. And as long as you write 6 correct things, you'll pick up the marks. But you must cover solids, liquids and gases. So I recommend thinking about 2 points for each of solids, liquids and gases. So here's the sort of thing I might write. I could include something about the fact that the particles in a solid, and again, I'd write in a solid here rather than just putting S at the beginning, so it's very, very clear. So particles in a solid, I could say, are regularly arranged. I could talk about them being very close. I could talk about them vibrating around fixed points. I could talk about the fact that they've got a lower energy. So plenty of things I can say there. When I'm looking at the liquids, I can talk about the fact that they are still touching. So they are still close. They're able to swap places. I could say there's more energy than in a solid. I could talk about the idea that the arrangement is more random. So plenty of things there. I can talk about energy, arrangement and movement. Once I get to gases, I can talk about the fact that we've now got high energy. So the particles are moving rapidly and randomly. And I can talk about the fact that they're very spread out. So I've written more than 6 marks there. But I've got all the information I need. Now, just to ensure that I hit this mark about using good English, the difference between what I've written and what you would need to write is you would need to write 4 sentences. But once I've got an idea about what information is going to go down there, then I can start writing. The particles in a solid are regularly arranged and closely packed. They vibrate around fixed points. The particles in the liquid have more energy, and although they're still touching, they're able to swap places, and the arrangement is more random. The particles in a gas have a lot more energy, meaning their particles move rapidly and randomly, and they are therefore very spread out. Hopefully what I've just said there shows you how to turn those notes I've made there into a high quality answer that's going to get you those 6 marks.